Okay, page 9 in your notes. Here's the data from one of the groups for the Barbie Bungee, but the group forgot to record their measurement for 5 rubber bands. So we are not going to go to Statlet. We're going to use our graphing calculator instead. So let's change that. We're going to use the graphing calculator. And we're going to use the graphing calculator not just to calculate what R is, but also to find the equation of the least squares regression line. All right, so I'm going to walk through this with you guys. Using the graphing calculator, first we have to do something that, unless the calculator gets reset, we won't ever have to do this again. But first we have to turn on the function that will allow us to see what R and R squared are. So on the calculator, I need you to hit second and 0. Hit second and 0. It should say catalog up at the top of the screen. If you look at the 0 button written right above it in blue, it says catalog. We push the blue button to access the blue functions. Does everybody see catalog on their screen? All right. We're going to go and turn the diagnostic on, which is in the D section. Now, if you just start scrolling through this, you're going to have to go through all the A's, and then all the B's, and then all the C's, right? So what we're going to do next is jump right to the D's, all right? If you started scrolling, that's okay. You can get there too. But I'm going to jump right to the D's and then scroll from there. So you push the X to the -1. Do you see how right above that there's a green D? If you press that, it'll jump right into the D's. And then we're going to use the arrow key and arrow down until you see the one that says diagnostic on at the bottom of the screen. You're going to hit enter, and it looks like this. Now, the calculator hasn't actually performed this function yet. So it hasn't actually executed it. You have to hit enter one more time, and it'll say done on the screen. Now it has turned this feature on. And again, you don't have to do this again unless the calculator gets reset. If you're using the app on your phone, I believe you have to turn it on, although I'm not 100% on exactly how the apps are set up like that, but you would have to walk through this process to turn the R and R squared on. Once we have that set up, now we can get to the part where we're going to make it calculate R and R squared and give us our equation for the line of best fit. So hit stat. Screen should look like this when you hit the stat button. Stat is by those arrow keys. So far, so good? All right. We want edit, so you can either press the number 1 or you can hit enter if the number 1 is highlighted. And there may be some numbers in these lists. We have to start by clearing those out so that we can enter our own data. To clear the data all out at once, you're going to highlight the name of the list. So I'm going to go up and highlight L2, and I hit clear and enter, and it wipes the whole list. And then I'm going to use my arrow key to come over to list 1. I'm going to highlight list 1, hit clear, and enter. And it clears everything out. Thank you. All right. So now we're back on page 9, looking at the data that's there. We have a number of rubber bands and a distance traveled for quite a few values on here. We're going to enter these as ordered pairs. The X's go in list 1, and the Y's go in list 2. Now, there's one of the X's that we have to leave out because we don't have a matching pair of information for it. Which X do we have to leave out? 5. So we're going to go 0, 1, 2, 3, 4, 6, and 7. So 0, you have to hit enter or the arrow key after each number that you enter. So 0, 1, 2, 3, 4, 6, and 7. Make sure that all of the numbers show up on the list. So either enter or arrow down after each number. And then you're going to come over to list 2, and you're going to enter the corresponding distance traveled for each of these. So 25, 32, 41, 49, 55, then we get to the one that we have to skip, but we already skipped the X that goes with it, so that's okay. And then 69 and 78. So far, so good? I want to make sure I'm not moving too fast for anybody. David, where are you stuck at? You put 5 on there. We don't have the data, the Y part for 5, so we have to take 5 off the list. So come up here, hit clear, and enter. Okay, let's move 6 here. No, just go on top of the 5. Push 6 and enter. Push 7 and enter. And then we need to clear this one out. Doesn't like it. I'm trying to clear that one number. Okay, so what you're going to do is you're going to enter 6 rubber bands. And then you're going to enter this one twice. That'll be the same dot on top of itself. All right. So everybody got their data in these 2 lists. All right. Hit the stat button again, the one next to the arrows, stat. And this time we're going to arrow over to the one that says calc. This will calculate a whole bunch of different things for us. We want this to calculate linear regression. We want a line of best fit, but we don't want it in AX plus B form. We want option number 8 down here, A plus BX. This is the one that gets used for statistics. It's like slope-intercept form, but twisted around the other way. They put the y-intercept first. So we want option number 8. I want my X list to be list 1. I want my Y list to be list 2. If those ever get cleared out, the way you put list 1 and list 2 in, if you look above the buttons 1 and 2, you'll see in blue L1 and L2. So you would push the blue button, the second key, and number 2 to replace L2. We don't want anything for a frequency list, and we're not going to store this, so then you come down to calculate and you hit enter. And it should look like this on your screen. So they're telling me the form at the top, and then they tell me the value that we're going to use for A, 25.333, or 25.33. We'll just round it off. Plus B, which is 7.46, and then X. And then notice it gives me my R squared and my R value. What would you say about the strength of this correlation? Very strong. It's a very strong, positive, linear correlation. Very strong, positive, linear correlation. All right, so let's go ahead and write this down. We're going to write our equation down. All right, so first I wrote down my form. And then I wrote down 25.33 for the A value plus 7.46x. Now, over top of the y, the graphing calculator won't show you this, but over the top of y, we're going to put this little caret over the top of y, like this arrowhead pointing up. It's called a hat. They got very creative with this. So this is y hat equals, and the hat on there means that it's telling me about predictions. Without the hat, we're saying we have gathered this actual data. This was measured data from when Barbie did her bungee jumping. With the hat, we're saying this is what my model predicts the distance Barbie would travel.
So would we not also do the squiggly lines because it also is approximate? It's not the exact data, but it's approximately what that prediction look like.
So I do understand what you're saying. We would not, the hat takes care of that. So we're going to use our model to come up with a prediction, but then we're going to use that hat to say this is what my predicted output would be, but not what my actual measured output was. The reason we're not going to use the about is maybe something weird happened and we actually end up with an outlier for this piece of data. In that case, my prediction would not be close to the actual output, but it could still be used to make a prediction about what's going to happen. All right. So here's the thing about writing equations in statistics, and this is why we use the form a plus bx. This is not the preferred way of writing the equation. We want to put what our variables are in this equation. We want to put the words in the equation, not just use x and y. So the way this equation should look when written in full is distance, that's my y variable, distance hat equals 25.33 plus 7.46, and then inside parentheses, I have what my x variable is, rubber bands. So when we write equations for lines of best fit in statistics, we want the names of the variables in the equation. And this is why we put the x at the end so that I have room to write a whole word.
Why are we doing the repeating symbol over the 3?
Why aren't we?
Yeah.
You could, however, it's going to be a lot harder to substitute in if we use the repeating symbol. So we're going to round it to 2 or 3 decimal places depending on what you're looking at. All right. I would like for you guys now to use that equation to predict the distance that Barbie traveled for 5 rubber bands. Use the equation that we just wrote to predict what the distance traveled was for 5 rubber bands. That's a good question. We can come up with just a single value, or you can put the hat over distance equals and then write the value there, yes. What'd you guys come up with? 62.63, yes. So here's the way I wrote mine. Distance hat equals 25.33 plus 7.46 times 5, because it did say to show work, so I'm showing myself plugging it in. And then my final answer, yes. Gotcha.
I can't give you y at all.
You should not. You should not. We want to use the names of the variables as much as possible. All right. One of the group members later found their measurement for 5 rubber bands was 64 centimeters. Was the actual value above or below the prediction? Above. The actual value was above the prediction. How far off was it? 1.37. So we had 1.37 above the predicted. What we just calculated is called a residual. The residual is the actual data value minus the prediction. So we use a little acronym RAP to help remember that. The residual is the actual minus the predicted. I would like for you guys now to predict the distance that Barbie would travel if the group used 20 rubber bands. Number 4, predict the distance that Barbie would travel if the group were to use 20 rubber bands. Yes. Where's your data? Hit enter. Okay, and then go to stat, go over to calc. We want option number 8. You have list 2 there. We want list 1. So second and 1. There. Now you have your X list in list 1 and your Y list in list 2. So come down to calculate. What'd you guys get for 20 rubber bands? 174.53. Would you trust that prediction more or less than the prediction that we made in number 2 about 5 rubber bands? Less. Why? I like what you're using. So I would say I'm going to trust it less because it's farther away from our collected data. My model is going to be pretty accurate as long as we stay close to the collected data. The farther out we get from our collected data, I can't promise that my model holds up that far out. My model works for the data that is near what I collected. This is called extrapolation. This is called extrapolation, when the data that we have is not close to what we are trying to predict.
Wait, so this wasn't up to personal preference?
Correct. This was not an up to personal preference thing. The farther away from the collected data that we're trying to make predictions, the less accurate those predictions will be. What is the y-intercept of our equation for our regression line? 25.33. That's my y-intercept. What does it mean? Well, think about the y-intercept as an ordered pair. Let's start there. What would the ordered pair for the y-intercept look like? 0 and then 25.33. So 0 and then the number for my y-intercept. What do we have x meaning here? Number of rubber bands. So when I'm talking about my y-intercept, it would be 0 rubber bands, right? And so then what's the y part of the ordered pair telling us about? The distance traveled. Now, if I'm using the y-intercept from the equation, is it telling me what was actually measured or what was predicted? What's predicted? We used the actual data to come up with the line of best fit. What was actually measured is 25, so we're pretty close, but 25.33 would be our prediction, right? So interpreting my y-intercept in context, when the bungee has 0 rubber bands, when x is 0, the predicted distance traveled, the predicted y value, is 25.33 centimeters. Correct. When we ask about the y-intercept, because there's a lot of data that we won't necessarily have a 0 collected data for, an input of 0, and so we'll use our y-intercept from our line of best fit to make a prediction about what that would be. Yes. What is the slope of our line of best fit? 7.46. What does that mean?
It's the bunches of the distance traveled between each rubber band is approximately 7.46.
Yes, no, I like what you're saying. I like where you're going. I would just change your language a little bit, but your idea behind it is absolutely correct. So every time we add on one more rubber band, because slope is talking to me about change. Slope is talking about the rate of change. The slope is the change in the y variable divided by the change in the x variable. The change in the y variable divided by the change in the x variable. So when I'm talking about the change in the y variable, what is it that would be changing? What is my y variable measuring? Distance traveled. And when we have a slope written in decimal form like this, not in fraction form, our denominator is going to be a 1. So the change in my x variable would be 1. And what is our x variable measuring? Number of rubber bands. So if I was going to describe this, explaining what it means, oops, sorry, that was not supposed to, sorry, I don't know why it's doing that. There we go, better. When we add 1 rubber band, the predicted distance traveled increases by 7.46 centimeters. How did I know it was increasing and not decreasing? Yes, because it's a positive slope. When we talk about slope, you always want to make sure to mention that this is a for each or for every. So as we go up by 1 in the x variable, what is happening or what is predicted to happen to our y variable? Yep, specifically in this case we would predict that it goes up by 7.46 centimeters. But that is a prediction. That is not a guaranteed outcome, so we want to make sure to talk about it being a prediction. Anything that comes from my equation is a prediction. All right. So this equation that we came up with, it can be called the line of best fit. It can be called a regression line, or a lot of times what it gets called is the least squares regression line, which we abbreviate as LSRL, the least squares regression line. And we will look later this week at why it's called the least squares. Actually, I think we're going to talk about that tomorrow. All right. All right. Let's look down at the bottom. Here is computer output for linear regression. This is oftentimes what you will be given to answer a question. And this gives you all the information that you need in order to write the equation of the least squares regression line, as well as to interpret some other important information here. So first thing I want to point out, it says constant and then it says rubber bands. This is my x variable. Next to the constant, we have a column here that says coefficient. The top one, the one next to constant, this is my y-intercept. This is a from a plus bx. Next to my x variable, that coefficient is my slope. This is b. We have y hat equals a plus bx. That is the form that we will write our equations in. Right here, this is r squared. That's the coefficient of determination. We will not use the one next to that that says r squared adjusted. We don't use the r squared adjusted, just the r squared.
Why is it adjusted?
I'll be honest, I don't know. I don't know.
Miss Fuller, you're supposed to know everything.
There is one other piece of this that I want to talk to you guys about, and it's this S right here. This is the standard deviation of the residuals. Nope. The standard deviation of the residuals. You can call it S, but you do need to know what that S means. So you will be asked to interpret what S means, what the standard deviation of the residuals means, and here is how we will interpret that. The actual, yep, squeeze it in down at the bottom. Squeeze it in. In this case, it would be the actual distance traveled typically varies by about 0.9 centimeters from values predicted by the least squares regression line, LSRL, with X equals number of rubber bands. So the standard deviation of the residuals tells me that the actual Y typically varies by about whatever S is from the values predicted by the least squares regression line, where X is the number of rubber bands. Right. You find a way to get it squeezed in? Okay.
Next year, we'll have to give more space.
I can put it to the side.
Yep.
Because
All right. You guys ready to go to the next page?
Yes.
All right, let's flip the page. So our learning targets for today. When we make predictions, remember Y hat, you'll actually put your Y variable name in here with the hat over it, equals A, that's your Y-intercept, plus B, that's your slope, and then instead of writing X, you're going to put that inside parentheses with what the name of your actual X variable is. And be cautious with extrapolation. If you've been asked to make a prediction about something that is far away from the collected data, it is suspect. Residual is actual minus predicted. The actual, whatever our context is, was whatever the residual is above or below the predicted value for X equals whatever.
I'm surprised you haven't said wrap in there. That's perfect for memory.
If I would say what?
Wrap.
Wrap? Yes. Actual minus predicted, wrap. Interpretations. When X equals 0, this is the interpretation for my Y-intercept. When X equals 0 in context, the predicted Y context is whatever my Y-intercept is. For my slope, for each additional X context, the predicted Y context increases or decreases by whatever the slope is. This idea that you get predicted into these explanations, into these interpretations, is absolutely vital. All right. Speaking of, down in the check your understanding, I would like for you guys to do number 1 and number 2 on your own right now. Here's our equation. And they tell us what y equals and what x equals. So I would like you to interpret the slope and then explain whether or not the y-intercept has meaning in this context. And if so, I want you to interpret it in context. If not, I want you to explain why. Use the front side. For the first one, I want you to interpret the slope of the regression line. You've got the equation. You have what x and y mean.
What is 160? What's the slope?
Oh, that's the question.
Can I have an
This is possible. It's a plus bx. A is your y-intercept. B is your slope. It's just like slope-intercept form. Y equals mx plus b.
So 20 is A and B is 160.
Yes.
So
And A is your y-intercept. B is your slope.
oh, it says that.
We got another minute to work on these two, and then we'll go over this part, and then we'll do the bottom part.
Wait, so his actual would be 760?
What actual would be 760?
Before.
To calculate the predict amount, so then the actual would be 760.
Yes. Yes.
It'd be a negative.
All right, let's interpret the slope of the regression line. What is the slope?
160.
160. And slope is always talking about a rate of change. It's the change in y over the change in x. This has been written as a whole number, so what is the denominator on this? 1. And that's my change in x. What is my x variable measuring?
The distance ran in miles.
The distance ran in miles. So for every additional what? For every additional mile,
He's predicted to burn 160 more calories.
yes, yes. For every additional mile that is run, or that Michael runs, the predicted number of calories burned increases by 160 calories. This predicted part is super, super, super important. Super important. On questions like this that show up on the AP exam, if you leave off that word predicted, it goes from being essentially correct to partially correct. So this is one of those big important concepts where one word being there or not being there makes a huge difference. Does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept. If not, explain why not. What is the y-intercept? 20. Yes.
Why did you say like the number of calories burned is increased by 160?
Well, the slope is 160. That's your slope. It's a positive number, so it would be increasing. If it was a negative number, it would be decreasing.
Well, like, why not know why is it X then?
Why not what?
Why is it not like this?
Because 160 is how many calories you burn per mile. So if you multiply how many calories you burn per mile by how many miles you get, it's going to increase based on how many miles you do.
The x variable here is the distance. The y variable is the calories burned. This is what's changing as this changes. So for every one more of these, how much is this changing? That's what the y-intercept, or sorry, that's what the slope tells you. The change in the y variable over the change in the x variable. And the change in the x variable is always going to be by 1. So your x variable will be changing by 1. The slope tells you how the y changes in response to that. That's what slope tells us. All right. Back to my other question. What was the y-intercept here? 20. So does that have a meaning in context?
I don't think so. I think it does.
I think it might. What's x measuring again?
Calories, how many no, how many calories?
X is talking about distance. X is our distance in miles.
Sorry.
So my y-intercept written as an ordered pair would be what?
0 to 20.
0, 20. Where 0 means no miles run. And the y-intercept part of that would be telling me what? How many calories burned. Not necessarily from running, because he's got 0 miles run.
How many calories he started with burnt.
How many calories he started with burnt, yes. Now, because this is coming from my equation, what important word do I have to get in there? Predicted. When Michael runs 0 miles, the predicted number of calories burned is 20 calories.
That was tricky because it talks about there's 20 training runs.
Mm-hmm. Yes, I agree. All right. I would like for you guys to do numbers 3, 4, and 5 now. Do numbers 3, 4, and 5 now. Take about 2 more minutes to finish this up. What is the predicted number of calories Michael burns if he runs 5 miles? 820 calories, yes. Calculate and interpret the residual if his Apple Watch said that he burned 910 calories on a 5-mile run.
This is 760.
760. I don't know why mine says 910. Let me fix mine. 760. Thank you.
Negative 60. R is negative 60.
R is negative 60.
Oh, because you, okay.
Yep, I got to fix mine. So R would be not 90, but negative 60. So how would you interpret that? Because it did say to interpret as well.
The actual calories burned was 60 calories below the predicted value for 5 miles ran.
Yes. The actual number of calories burned on a 5-mile run was 60 calories less than predicted. Michael is thinking about signing up for his first marathon. So far, his longest run has only been 10 miles. Should he use the regression equation to predict how many calories he would burn if he runs a marathon, 26.2 miles? No, why not?
He's not trustworthy because it's farther from the cliff.
Yes. So I would say no. 26.2 miles is far outside the data he has collected. This is extrapolation, so it's less trustworthy predictions.
How do you know what the cutoff is for that? Like if it had said like 19 or like 20.
So if his longest run has only been 10 miles and he's only been tracking it for about that far, I probably wouldn't go out any further than like 12 miles for a prediction. But we could make predictions like, say he's done a 5-mile run and a 7-mile run. I could make a prediction about a 6-mile run even though he hasn't actually run it yet, because that's in the middle of what we have data for.
As long as it's within
Yeah, you want to be relatively close to your collected data, preferably within your collected data. All right. Homework is due on Thursday, which is in 2 days. Homework is due on Thursday, which is in 2 days.